So good morning, everyone. So as you notice here, today we start with the topic of EM waves. It's not a big topic. Just 3 days we will finish it. Okay. And EM waves essentially see this idea of EM waves. Basis is Maxwell equation and Maxwell derivation. And this was the his work started. Actually his work only gave the insight into idea of EM waves. What does EM wave stand for? Electromagnetic waves. So he combined both electric properties and magnetic properties together. And by combining those two properties, he could prove that light, what we see, is nothing but electromagnetic field oscillation. We'll try and understand what that is. What he did, what we call as Maxwell equation. Maxwell equation, these are he collected the known laws related to electric field and magnetic field. What are the known laws related to electric and magnetic field? See, we know one is Gauss law. So this one is, what is this one? We can call this as this is surface integral of electric field or flux. So one of them is surface integral over a closed area is equal to Q by epsilon naught. In a similar way, though there's no law for magnetism, I think we briefly discussed. If a similar way we can do, even this law also is valid. Only difference what you notice here, this also surface integral of electric field, surface integral of magnetic field over a closed area. This also equal to charge enclosed by epsilon naught, and here also actually is similar. It is equal to magnetic charge enclosed by epsilon naught. Since magnetic charge or magnetic monopole cannot exist, this is zero. So what we notice, these two laws are very similar. What happens for electric field? Similar thing is valid for magnetic field as well. Then he continued further. This was surface integral. We also have a line integral. Line integral EMF for a closed loop is equal to E dot dl. So this is something, this is Faraday's law. Line integral of electric field along a closed loop for open surface is equal to minus d phi by dt. So here this electrical field was connected to electrical charge. But what we notice here, this law connects electricity with magnetism. What is causing this electric field here? Electric field is being caused by magnetic properties. That's provide the link between the two. So this was in case of surface integral of electric field, surface integral of magnetic field. Similar way, we have line integral of electric field. Of course, the next one is going to be line integral of magnetic field, which is Ampere's law, which is equal to mu naught by I. So when he looked at that, he felt these two are consistent. Similar way, the way electric field is related to change in flux of magnetic field. If these two similarity, if similarity were to exist, even this also the term which should have come here, and what should have come here? Here also on the right side, something like this should have come if there was symmetry. This kind of term with the appropriate dimension should have come, but which was not there. Then he started thinking why it is missing, and he started analyzing Ampere law. And based on some analysis, he could prove that Ampere law in this form is not correct. It needs some correction. It was just theoretical calculation and using some. So we'll look at what is the correction he made. So Maxwell equation are same known equation. Only thing, looking at this equation using the idea of symmetry between electric field and magnetic field, he said, okay, this equation seems to be not symmetric to the previous one, so may need some modification. So before we go into modification, we are talking about flux. So again, we'll go through the idea of flux very quickly. If suppose we have there's a field like this, and what is the flux through circular area of radius r? So if I have a circle which is of radius r, and it is placed with axis along x-axis and field also is along x-axis. What is the flux? We know the flux is equal to dot product of field and area vector. And if area is a plane area, entire area will have same vector. What is the flux in this case? Flux in this case is equal to E into area. Because cos theta term equal to 1 when field is perpendicular to area. This we know already. And if I have to define this surface, is this an open surface or closed surface? If I take a circle, I hope all of you understand what is closed surface. Closed surface encloses some volume. This is an open surface. It's a plain open surface. So this will keep in mind because we are going to understand Ampere law. Ampere law is based on something like line integral along the boundary of the open surface. That's the loop. So line correct the understanding of Ampere law is it is line integral around the boundary of the open loop. So if I take this open surface, this boundary forms the Amperean loop. I can flux. Let's take another case here. What is the flux through open cylinder? So this time I have taken a circular area. Now I'm taking open cylinder. What is open cylinder? This is a, just assume that it was a closed cylinder. If one surface is removed, the cap of the cylinder is removed, this becomes an open cylinder. What is the flux through this open surface? This open cylinder. Flux to this open cylinder. It has now two surfaces. This is open, so this surface is not there. This surface and lateral curved surface. We can think of a flux also in terms of how many field lines are passing through the surface. Field lines are going to pass only through this surface here, which is same as this surface here, and no field line is going to pass through the curved surface. So we know in this case also flux is same. So we understand the reason I'm explaining this one. We are going to use it in the next slide. So this is an open cylinder. I hope all of you understand what kind of surface this one. This one also is an open surface. So can this surface form and can we use this surface to apply Ampere law? We can apply. But what is the boundary of this surface and this surface? What you notice, the boundary of this surface and boundary of this surface are identical. What is the boundary of this surface? This is not the boundary. The surface doesn't end here. What is the boundary of this open surface? This is the boundary of open surface. So if I have to take this as a surface, the boundary of open surface will be this. When I calculate, when I apply Ampere loop rule, I will calculate B dot dl along this path and the surface will be like this. So let's see how we apply this case. So both are open surface. It meets the requirement of Ampere law. I can apply Ampere law for this surface also, I can this surface also. And that's what we're going to do. Okay. So if this is the surface here, one I have taken a circular surface. If I take with the same boundary, I have taken a cylinder or any surface if I take which is which surface terminates in a circular boundary, all the surfaces, the flux will be same, whatever surface we take. Let's see what we are talking about. So let's try and understand how did Maxwell prove that Ampere's law is incomplete or incorrect. Okay, so just imagine, so you have a capacitor. These are the two plates of capacitor. We have taken circular plates because of symmetry. So this is a parallel plate capacitor and two plates are circular in shape. It is connected to battery. When it is connected to battery, it will start charging. It will start receiving charge. So let's say, so this capacitor is getting charged. When capacitor is getting charged, it means some current is flowing through. And if current is flowing, it means the charge is getting added to the plate. This is a plate here, which has positive plate charge. And this plate will have negative charge. And of course, the charge will lie on the inner surfaces here. Okay. So this is something, we apply Maxwell law here. Okay. Sorry, we apply Ampere law here. And then we notice what is the area where it is incomplete or incorrect. Okay, so let's say suppose there's electric current flowing here. This part is electric current flowing here, and wherever there's electric current, it will create magnetic field around it, and I can apply Ampere's loop rule. Let's apply Ampere loop rule and we apply to charging capacitor at a point P. I want to calculate field at this point P. So what we have taken an Ampere, we have taken Amperean surface, open surface. What is surface we have taken? I have taken a circular surface similar to the previous slide. So this is the first I have taken this surface. This is circular surface. So if can we apply Ampere loop rule here? Well, yes, I can apply Ampere loop rule. This is the boundary of the surface here. This circle forms a boundary. How do you apply loop rule? See, because of symmetry here, if you look perpendicularly, this is something. So if Ampere loop rule, since the current, the loop is symmetric about the current element, everywhere field will be tangential to the circular loop here. Since the magnetic field is tangential, B dot dl, angle between B and dl vector will be equal to cos theta will be 1. So B dot dl and along the whole loop will be equal to B into 2 pi r. This is what we had done earlier also in case of Ampere law. So line integral of a magnetic field along the boundary of this open surface is equal to B dot B into 2 pi. I'll repeat again. What I am calculating here? We are line integral of magnetic field along the boundary of an open surface which is in form of a circle. So boundary also is circular. It's a surface is like a circular disk. It's equal to mu naught I right hand side. What is the right hand side? Right hand side is mu naught into current passing through the surface. Yes, this current is passing through this point through the surface. What is the current passing through? If IC is the current here, which is coming to the capacitor, same current is passing through here. This is mu naught into I. That's how we apply Ampere law to this surface here. What Maxwell did, he take, okay, let me keep the boundaries same. Let me keeping the boundaries same, let me change the surface. Now, what is second type surface he chose? He chose a surface which you can think of something like an ellipsoid. This is surface it took. The boundary remaining same. Or I hope some of you noticing this boundary remaining same. He took a different surface. Now consider a different surface having same boundary. So since the boundary is same, left hand side the equation is going to come same, no change in this part. Left hand side will come to same. But now what happens, the boundary is, this surface is like this, and this boundary is enclosing the one plate of the capacitor. So is there any current which is passing through the boundary here? The current passing through boundary becomes zero. The right hand side of the equation becomes zero. So what I find, one case, same boundary, if I take two different surfaces, and we are getting inconsistent result, which clearly indicates there's something, Ampere's law is incorrect. Yes, Vignesh?
Sir, while using this law, we should take only the current that is like cutting through the across the boundary.
Passing through the surface.
Yes, sir, but the same current is passing through the surface, right, sir?
Is it passing through? If I take a surface like this current here, this surface is where the surface here. Are you able to visualize how the surface is? I will take one more shape later on. So is this current passing through this? The current stops here at the capacitor. So if I take a surface which includes one plate of the capacitor, no current is passing through. Are we clear about this part? If not, I will second slide. This is something I'll say. I will take one more example, so perhaps you will understand better also. So what in it is this inconsistency. So in this case, same boundary. If I take this circular disc surface, current is passing through. If I take this curved surface, just imagine it's a hemisphere. So what is this first surface? I have taken circular shape. If I take this circle plus curved surface put together, it forms a closed surface. But if I take circular surface once and hemispherical curved surface next, both are open surface but have a common boundary. Both are open surface but having a common boundary. Current is passing through the circular surface, but current is not passing through curved hemispherical surface. Is making sense now? Okay. Yes, so now like this, but this surface, there's something. Current is not passing through, but you know, when there's a charge on this capacitor plate, there's a field existing between two plates of the capacitor, and this electric field lines are passing. So what is happening? Though current is not passing, current passing has become zero through the second curved surface, but something else is passing through the surface. What is passing through that surface? Electric field. So there's an electric field flux through the second surface, which is not there in the first surface. So what we notice here, keeping the boundaries same, if I take two Amperian loop having common boundary, one Amperian surface which having common boundary. So loop is common, but surfaces are different. So B dot dl term has to be same because B dot dl is calculated along the boundary of the surface. If I take a circular disc kind of surface, current passes through. If I take curved hemispherical kind of surface, current is not passing through, but field is passing through. Then he said, okay, let me calculate what is the field passing through and what is happening here. So let's understand second part. Now I will draw the figure in slightly different way. If somebody else has any query?
Sir?
Yes?
Sir, can't we only apply these laws when the charges are at a long distance?
No. I'll come to that part. No, see, this is something, see, I discussed something before we discussed Maxwell modification. And when we discussed that time, I also mentioned, okay, well, I'll just go through this part, you'll understand that part, okay? Let's see, now we consider, again, let's take a slightly different shape. So same thing now, rather than curved surface, what we have done, I'm using the same cylinder analogy. Are you able to visualize what is this orange surface indicate? How do you define this orange surface here? What is the orange surface? Is it open surface or closed surface? It's a one side open cylinder. That's why it is open surface. Okay, so if I have to calculate, can I calculate electric field flux through this surface? And the current here is I. If current is I, the charge on this plate is equal to Q. That's the charge on the capacitor. And if there's a charge on the capacitor, there are field lines from positive plate to the negative. There's electric field here. Okay, so this is in 3 dimension. All of you should be, I think if you're able to visualize, this is how the field lines are from positive plate to negative plate. Can we calculate electric field flux through this open cylinder? Curved surface, there will not be any electric field flux. There will not be any flux. Flux will be only through this one end of the cylinder, which is circular in shape. And the flux will exist only in the part of the area which is which this part of area only will have field. Are you understand? So which part of this circular area will have electric field? Only the area which is parallel to the plates of capacitor and same radius as the plates of the capacitor. Hence this area is equal to area through which field lines will pass. So this area will be equal to area of capacitor plate. And if I take this surface here, field lines will be perpendicular to surface and flux will be equal to E into area. So if I take this surface, what is the flux? Electric field flux is E into area. And what is the field? If charge is Q, or okay, I can write as Q, small q is capital Q, charge is Q by, so field is equal to charge by E epsilon naught. Thus the formula of field between the plates of capacitor. So flux through this the circular surface will be equal to E field into area of capacitor plate. And how about this part? The part which is larger than area of capacitor plate. This part no field and has no flux. So what is the flux equal to? Flux is equal to E into A being the area of the capacitor plate. So this is the value of E. So if I write, it is Q by epsilon naught. That's the electric field flux. So that is the flux which is passing through. Then he said, okay, what is the rate of change of flux? So here also in case of, okay, as the charge on capacitor is changing, when the capacitor is getting charged, if the current is flowing, it means charge is increasing. This Q also will remain constant if we keep on increasing. So if we calculate rate of change of electric field flux, d phi by dt, this term, if I differentiate, this term becomes equal to, if I differentiate, it becomes I in, dq by dt is equal to I by epsilon naught. And this we notice here, the I term has come here. And what is this I equal to? This I is equal to current which is coming into the capacitor. So we are getting an I term here. So what I notice here, and this term is current, and this current also, this coming as I, but where is this current? This term I has come because of change in electric field flux through this area. So what is causing this current? This term I has come, and this current we call as, this current is called as a displacement current. So what is displacement current equal to? Displacement current is equal to epsilon naught into d phi by dt. So what it says, this is okay. So let's say, so what is this ID? So this is the correction what he made. Let's look at the equation now. He made this correction here. B dot dl should not only be equal to mu naught I, it should be equal to mu naught I plus ID. And what is ID equal to? So ID is equal to, so actually I could have written this term, just think of it, I can write like this. This current is a conduction current, and this current is called displacement current. And what is giving rise to displacement current? Change of electric field is called giving rise to displacement current. So this is the generalized form of the law. We can write in any form, like I said. This is generalized form of the law, and this term here is having same dimension as current, and this term is called displacement current. So he has added one more form of current through the surface, which is called displacement current. There's something like a time constant. Okay, it has same dimension, and what we notice here. So what does this equation tell you? This term has similar effect as I. So in terms of words, we can say varying electric field produces same effect as conduction current. So if I take, so what is B dot dl equal to? Either the field is created either by the current passing through this B dot dl term is created either by the current which is passing through the surface, or it can also be caused by change in electric field flux passing through the surface. So change in electric field flux through a surface gives rise to same effect as current passing through the surface, and hence this term is called displacement current. What is displacement current? Okay, so displacement current. So let's try and understand this displacement current. What is displacement current? One thing we have to keep in mind: displacement current is epsilon naught into d phi e by dt. So let's say if we have to find displacement, you know, the current term. What is term of what does current mean? Current is always through an area. Current is a charge passing through area. In case of displacement current, we are talking about first electric field flux through the area. And if this electric field flux is changing, that also creates an effect equivalent to current. So if I take a smaller area here, if I take a small area which is radius is less than the radius of capacitor plate, what would be the previous case? What would be the displacement current through this area? Okay, so that's what we are trying to understand. How do we calculate displacement current? So when you see what we understand, flux, electric field flux through entire region between the plates of the capacitor, field is uniform. And field is, if I take an area parallel to the plates of capacitor, flux through any area will be E times that area. So flux will be E into whatever area bound by that radius. So what do you understand? The electric field flux will be proportional to area. Hence, rate of change of electric field flux also will be proportional to area. Hence, displacement current also will be proportional to area. Final statement I'm making: if displacement current is proportional to area, it is equivalent to displacement current uniformly distributed over area of capacitor plate. So how is the displacement current? I can think of displacement current is distributed all through the area of a capacitor plate. ID will be proportional to area. So displacement current is uniformly distributed over the cross-section area of circular plate of capacitor, and it is equivalent to conduction current. So if rest of this thing is a proof, which if you understand and don't understand also, this proof may not be very important. What is important? Have we understood this point? What is, and first of all, what is displacement current between plates of the capacitor? I don't have to calculate displacement current here. I know the formula, but displacement current is equal to current coming into the capacitor. Displacement current is equal to conduction current. So if I know this conduction current, I don't have to calculate. But this conduction current is coming through a small wire. How is the displacement current flowing through? Displacement current is getting distributed over the entire cross-section area of capacitor plate. So it is equivalent to this entire current I divided by area of the capacitor plate. That's where the current is flowing through. So we have to imagine displacement current as current equal to conduction current, or the current which is coming to the plate of capacitor, that is equal to displacement current. But it is uniformly distributed over plate of the capacitor, provided E is uniform. In most cases, E is uniform, because based on that only we have taken proportional to the area. Okay. So suppose somebody asks you, if conduction current is equal to 4 ampere at an instant, what is the displacement current between the plates of the capacitor? If conduction current is 4 amperes, what will be the displacement current between the plates of the capacitor? Arish, can you tell me what will the displacement current between plates of the capacitor if current coming to the capacitor is 4 amperes? How much will be the displacement current between plates of the capacitor? What we said here, displacement current is equal to conduction current. So here also current is equal to 4 ampere. But where is this current flowing through? Current is on this current of 4 ampere is distributed over entire cross section. So any circular cross section, if I take equal to area of the circular plate of the capacitor, current passing through this area is 4 ampere. Anvita, have you understood this point?
Yes, sir.
So we understood. So whatever current comes to the capacitor, displacement current between plates of the capacitor is same as the current coming to capacitor and uniformly distributed. Now, can you answer second question now? So if a radius of plates or capacitor is R, if I take another small area equal to R by 2, what is the area I have taken? I have taken R by 2 parallel to plates or capacitor. Can you tell me what will be the current through this area of radius R by 2? How would you calculate displacement current through a smaller area? Anvita, can you tell me what will the current through smaller area? If I take an area equal to area of the plates or capacitor and parallel to it, the current is equal to 4 ampere, but current is uniformly distributed. If I take radius is equal to R by 2, what is this area? This area is 1/4 of the area of the capacitor plate. If area is 1/4, what will happen to current passing through that area? That area of current also will be 1/4. So displacement current through any 1/4 area of the capacitor. So any area if I take parallel to plate of capacitor, if this area is 1/4 of the plate of area of the plate of the capacitor, the displacement current also will be 1/4 of the conduction current. It need not be concentric. Reason area can be anywhere. Any area if I take, field is uniform, charge is uniform, so all equal areas will have equal flux and have equal rate of change of flux as equal displacement current. Tejas, is this understood?
Yes, sir.
So I by 4 will be equal to displacement current through radius R is equal to R by 2. What will the Tejas, can you tell me what will the displacement current through a radius which is 1/3 of the radius of how much will be the current now?
It will be I by 9, sir.
It will be I by 9.
Yes.
And if rather than plates being circular, what happens if plates are square? Can I apply the same concept there also for square parallel plate capacitor?
Yes, sir.
Because there also what you have to check, when the square plate capacitor also, is the field uniform between the plates? There also field is uniform. Only condition being as long as field is uniform. So flux also is proportional to area. Rate of change of flux also will be proportional to area. Hence displacement current also will be proportional to area. So pretty simple. So whenever you have to calculate flux, you can easily calculate in this fashion. Now let's understand something about it. Now, if there's displacement current, what does Maxwell law say? His correction says even displacement current produces same effect as conduction current. As conduction current creates a magnetic field, even this also displacement current also creates a magnetic field. So the way we can find magnetic field for this, applying Ampere's loop rule, we can find magnetic field between the plates of the capacitor also applying Ampere's law. And you know how was Maxwell law verified? Because if we take as a conduction current, we can calculate conduction current at different points. We can calculate magnetic field, and magnetic field calculated using Maxwell modification matched with actual field. So there was several experiments conducted which proved validity of Maxwell equation. So let's calculate. How would he calculate field at any point between the plates of capacitor? So next point is we understood displacement current. What gives rise to displacement current? Change in electric field flux through an area gives rise to displacement current. It is equal to epsilon naught times rate of change of electric field through that area. For a capacitor, total displacement current is equal to conduction current. And if field is uniform, the displacement current is uniformly distributed over area of capacitor. This is the points we made so far. Now we are calculating magnetic field in the space between plates of the capacitor. Okay. Plus it is charging. And unless if I is 0, there's no displacement current, no magnetic. All cases we are taking the capacitor is in the charging state. It means the charge on the capacitor is changing, or there's a current here. If there's no current here, there's no displacement current, no magnetic field. So let's find, if I have to find field at some point P here. How would I find field at a point within the region bound by plates of the capacitor? This point P could be within R could be less than capital R, or R could be greater than capital R. And this calculation very simple. I'm going to use this equation. This is just a modification. So if we have to calculate, I can B dot dl can be calculated, and it can be equated to these terms. In this area, there's no conduction current. So when we apply Ampere Maxwell law for space between plates, this term becomes 0. Actually, I'm calculating only this term here. So how do we calculate here? So I can treat even this space between plates of the capacitor as having current, just like previous cases we had done. And how is this current? Current is uniformly distributed. So I can take what is the current density in that case. Current density will become I divided by area of the plates of the capacitor. So this situation also is equivalent to current flowing through a circular cross section of radius r. Current is uniformly distributed. And we have calculated field. Suppose I want to calculate field at this point P. The current is flowing like this. And this is at a distance R. And if I have to find field point P, how did we calculate field at this point P using Ampere law earlier? If first of all, if field is which direction the magnetic field is created, magnetic field which is created is perpendicular to electric field. Electric field is flowing along the axis, hence magnetic field is perpendicular to the axial direction of capacitor. So here the field may be like this, field everywhere this field is like this. So what was the how would I calculate magnetic field B here at point P at a distance r? This is the Amperean loop we had taken. So if I calculate this B dot dl is easy. B dot dl will equal to B into 2 pi r. And that will be equal to mu naught into current enclosed. And in this current enclosed also, what is the current enclosed? I can take current enclosed will be J into area. So current enclosed will be J into pi r square. Okay. So what you notice here, this situation is very similar to, we had done a calculation of magnetic field in case of long cylinder carrying current which is uniformly distributed. This situation is identical to that. Okay, so what will the field will be? This is J into pi r square. We substitute this term. What is J value? We substitute this term J value. J is equal to I divided by pi r square. So what I find, the term magnetic field at a distance r for r less than capital R is equal to mu naught I by 2 pi r square. How is this field varying? How do I define, what do you understand from this expression? How is this field varying as a distance r from the center of, what is the center here? Center is axis of the circular plates of the capacitor. It is varying linearly. And this was exactly the case we had in case of long cylinder kind of current carrying element. So B is varying linearly with R. So where would B become maximum? When R is maximum. On the surface at a distance equal to radius of capacitor, field will become maximum. So field will be maximum at R is equal to capital R. And what is the value of field? Mu naught I by 2 pi R. Have you seen this expression before? Mu naught I by 2 pi R. And no surprise, why it is coming as mu naught by 2 pi r? Because the total current is equal to I. And so if calculate field at, suppose we have to calculate field at this point, which is at a distance equal to r from the center. So if I take an Ampere loop, the current enclosed is equal to total current. That's why it becomes equal to I. It is same formula what you seen earlier. So actually this formula is very similar to what we had done in case of current uniformly distributed or cross section of a long cylindrical shape carrying current. So, and how would you, what would the field at a point which is greater than R greater than capital R? When we take R greater than capital R, what would be the value of displacement current enclosed? If I take an Amperean loop for R greater than capital R, what will be the value of, what will be the displacement current enclosed? What will be the value of displacement current enclosed? Okay, let me ask, Kaushik, can you tell me what is the value of displacement current enclosed through a circle of radius greater than radius of the capacitor plate? Kaushik, can you tell me what will be the displacement current? Kaushik? No idea. Okay. Tejas, what will be the displacement current?
It will be the conduction current, sir.
It will be equal to conduction current. Is that difficult to figure out?
No, sir.
So basically what happens is this one, the moment it becomes equal to conduction current, field at any point outside, it becomes similar to what is there due to conduction current. And what is the field due to conduction current? This is the formula. mu naught I by 2 pi r. So no surprise, outside it becomes take the shape, the same equation as conduction current. It is varying as 1 by r, and within, where does it become maximum? It becomes maximum at a distance r equal to radius of circular plate of the capacitor, which is equal to mu naught by 2 pi r, and from axis to this point it varies linearly. How would shape, if I plot the field versus R graph, this is how the shape would look like. This will be proportional to 1 by R. And this is very easy to remember. It is mu naught I by 2 pi r. So what is the maximum field anywhere between the plates of the capacitor? All cases you are taking circular plate. Then only you can take advantage symmetry. Everywhere at a distance r, we can take B to be equal. Without symmetry, we cannot take. So those who have find it difficult to understand all the derivation, let's look at in simple form what we have to understand. What we understand here, the conduction current, again to repeat, what is the conduction current equal to? Sorry, displacement current equal to conduction current. Uniformly distributed over the surface. Okay, so we can calculate conduction current. Area is 1/3. Displacement current also be 1/3 of the conduction current. If radius is r by 4, displacement current will be equal to 1/16 of conduction current. We understood that part. Second part, when we have to calculate field, I'll just calculate field at a distance r equal to capital R. Where I'm calculating field, just at a distance r is equal to capital R, and this is the value of field. This is the value of field, and that's the maximum field. Now, if I calculate this field now at any other point, I can easily tell you what the value of field is. Now, using this graph, let's see, those who understand this graph, let's try to understand. What is the field at r is equal to capital R? It is given here, mu naught I by 2 pi r. Now, if I ask Pranav Soma,
Yes, sir.
are you awake? Yes. Can you tell me what will you understand what does this expression mean?
Yeah, field at a distance r by 2.
So what will the field? Can you tell me from this figure? It varies linearly.
Yes, sir.
So at a distance r, whatever value of the field is, at a distance r by 2, what should be the value of field?
Half of it.
Half of it. This will be, so if I call this as B max, maximum field, it will be equal to Bm by 2. Is that difficult, Pranav?
No.
And if I, Shravani, you tell me now, if I say at r is equal to r by 3, what will the value of field at a distance r by 3, Shravani? In terms of maximum field? Shravani?
Yes, sir.
What will the value of field at a distance r by 3 from the axis of circular plate? Can you tell me?
B by 3.
B by 3. It is varying linearly. Now this is the point, so any point you can easily tell. Now I'll come to point which is outside. You understand what is 1 by r. So at this is at what, this is r is equal to, this is r. So if I take another point at a distance of 2r, and at 2r, Disha, what will the value of field at this point at a distance r is equal to 2r?
Bm by 2.
Bm by 2. And what will the field at a distance of 3r?
Bm by 3.
Absolutely simple. So if calculation, so now Disha, are you clear? Is calculation of field very simple?
Yes, sir.
So what we need to do for calculation of field, if I calculate value of I will only calculate maximum field, which is there at a distance r. Anywhere within less than that, it is varying as, is increasing linearly with r. Afterwards, it's decreasing linearly with r, and you can easily calculate. So at this point, it will equal to b by 3. This will become equal to b by 2. Similarly, if I take this point here at r by 3, this also become b by 3. Kaushik? Acha, you raised your hand. Khyati,
Yes, sir.
are you following?
Yes, sir.
So you are easily able to tell me now. If I ask you, suppose this question comes, the current, okay, what is the field at a distance r is equal to 1.5 r? How would you calculate field at a distance r is equal to 1.5 r? Can you tell me the method? How would you calculate? Khyati, can you figure it out or not so clear?
Sir, not so clear.
Not so clear. Okay. Bhagyashree, can you tell me how would you calculate field? at this point?
The R is greater than the max.
So first thing what we notice, R is greater than capital R. So which region it is lying outside? It is varying as 1 by R. And we have seen so greater than R. So then next step, how would you calculate?
So it's varying inversely to the R. So
Inversely to R, correct. So first what I should do, what should I calculate first? I should calculate
max.
No, maximum field is easy to write. Same formula as for line charge, which is equal to mu naught by 2 pi r. If it is at a distance of 1.5, so field will become Bm by 1.5. Is that difficult? And same thing I have written here also, using only B is equal to R. This formula, how do I calculate? Method is very simple. It is maximum at R is equal to R. For R less than R varies linearly. At R by 3, it will become 1 by 3 of Bm. At greater than R varies inversely as R. So when it varies inversely as R, if I choose 2 points, both the points chosen must be equal or greater than R. If I choose 1 point at R, other is BR. So BR by B capital R will be equal to capital R by small r. Using this formula, I can calculate field at any distance R. For example, at R is equal to 3R, what will the expression? Expression will be equal to BR by R will equal to, and this R will come here. It is inversely proportional. This R goes here. So it becomes BR by 3. So we can easily calculate. So calculation of conduction current. Calculation of conduction current through a smaller area or larger area between the plates of the capacitor is also easy. Calculation of magnetic field, maximum value of magnetic field is easy. Calculation of magnetic field at any distance from axis also is easy. Is that okay? Pranav, are you clear about all these points so far?
Yes, sir.
Dhanshri?
Yes, sir. Clear, sir.
Clear? Shreya?
Yes, sir.
So if I ask you, can you repeat all the key points? I'll repeat all the key points once, and all of you listen carefully. And that's how we maybe mentally also you should do that. See, this is what we said here. First thing, what is displacement current between plates of the capacitor? Is equal to current coming to the plates of capacitor, conduction current. How is the current distributed? Current is distributed all uniformly over the surface of plates of the capacitor. So what will be the displacement current through an area which is half the area of plate of capacitor, half the conduction current. If area is 1/4, displacement current will be equal to 1/4 of the conduction current. So current through any area between the plates of capacitor is in proportion to that area. So that any area we can find displacement current. How about field between plates of the capacitor? Field is maximum at R is equal to capital R. For distance less than R, it varies linearly. For a distance R greater than R, it varies inversely with R. And using this, we can find out. So calculation of magnetic field will only calculate Bm. And then we check whether R is less than capital R or R is greater than capital R. And if we understand this relationship, we can easily find field. So calculation of displacement current through any area, calculation of field at any point, any distance from axis also is easy. That part we are done. Magnetic field formula I'll use. Okay, now the question comes sometimes, how do I calculate this current coming here? This current also, I think the calculation of current is you need the knowledge of what we had done earlier. This current could be created by a DC source during charging process. It can also be created by AC source. And if you know those formulas, we can easily calculate. In case of DC source, if there's a resistor R, if we connect it up, this is how the current is if in case of RC circuit. The current is equal to I naught e raised to power minus t by tau, and tau is equal to RC. And what is I naught here? I naught is equal to, what is I naught here in case of RC circuit? It will become E by R. So in case of DC circuit, if they say what is the displacement current at time t is equal to tau, what is the displacement current at time t is equal to tau? Displacement current time t is equal to tau will be equal to conduction current at time t is equal to tau. And at time t is equal to tau, the conduction current is equal to, how much is conduction current is equal to 1 by E. So if I put the value of t is equal to tau here, it becomes equal to I naught by E. And I naught by E is roughly 0.37 I naught. Okay. For AC source, AC source also, how do you calculate current? Current is this term. Current in that case, current is equal to something like this. So what is the maximum current in that case? Maximum current will be equal to, if you have to calculate. So what is the maximum displacement current if it is connected to AC source? How do you answer what is the maximum displacement current? What will be the maximum displacement current? Maximum displacement current will be equal to maximum conduction current. So from this equation, I need to find maximum current. What is maximum value of current in AC circuit? Maximum current is equal to maximum voltage by, if only capacitor is connected, XC, or value of impedance Z. So this will maximum current. Suppose they say this will be equal to maximum displacement current. So maximum displacement current, displacement current is maximum when the conduction current is maximum. What is RMS value of displacement current is equal to RMS value of conduction current. What will the RMS value? V RMS by X. So they are depending on the source. To find displacement current, sometimes we need to find the conduction current first. Once we find the corresponding conduction current, that is equal to displacement current. So that is a AC source and DC source. Okay. So with current known, ID can be calculated and B also can be calculated. So sometimes this also additional thing we need to work out. That's all we had for this session. Now rest all is application. So 2 parts here. Yes, the Vignesh.
Sir, we are assuming that some displacement current is flowing, but nothing is actually flowing, right, sir, through the capacitor?
What is flowing through that area? We just made one statement. I'll repeat that statement again. Electric field flux. See, what is it? It's okay. What you say is right. Charge is not flowing through. Something else is flowing through. What is passing through that area? Electric field is passing through that area.
Yes.
Electric field passing through the area does not produce similar effect as current. Something else is produces similar. What is similar effect produces? If electric field flux passing through an area changes with time, it produces similar effect as current passing through that area.
Yes.
Is that understood?
Yes,
and there's no difference. As far as effect is concerned, both produce identical effect. So if I take here, if I take a region here, this is the area where only conduction current is flowing. If I calculate field at some point here, and here the displacement current is flowing here. If I calculate field at equal distance, both fields are identical.
Yes.
What I will show the effect of conduction current and something which has been defined as displacement current. Why we define as a displacement current? Are you understanding? If I ask you why this has been used as a current with those no charge is flowing.
Similar effect produces.
Similar effect. It produces similar effect. So there's no need for charge to pass through an area to create magnetic field. And there's another important point. To create magnetic field, so far what is that? Okay, to calculate to create magnetic field, charge has to flow. Charge has to flow means mass also has to flow. Without mass, charge cannot exist. Now what you're saying is something different. This is a little different. What is saying here?
Yes,
in this
so
case,
here change in the electric flux is producing the magnetic field.
So there's no charge necessary in a space or no charge motion necessary in this space to create magnetic field. And that's how people understood, okay, this EMF, this can be magnetic field can be created without any charge being present. And that's how EMFs travel through the space. So that's the reason. Okay. So again, to understand, the key part here to understand was, we understand current. Current through an area is rate at which charge flows through. We define another thing which also has a similar effect as a current. What is flowing through that area? If you have to define displacement current through area, what is flowing through? Electric field flux is flowing through that area. And rate of change of electric field flux through that area multiplied by epsilon naught. Why are multiplying by epsilon naught? Then only you get a current dimension. Then it becomes like a current. So what is the current equal to? What is ID? ID, that's what you understand. ID in terms of formula is simple. Formula is d phi by dt. And when we take d phi by dt, what you notice here, rate of change of electric field flux, what it is creating is magnetic field. And previously, as per the Faraday law, what creates E? Rate of change of magnetic field flux. Now there's a symmetry. And notice the symmetry between this. So what is causing magnetic field here? Change of electric field is causing magnetic field. What is causing electric field here? Change of magnetic field was causing electric field. So they are something, they have this kind of symmetry between the two. Anvita, have you understood what I said here? Anvita?
So not clearly, sir.
Not clearly. Okay. So in case of, as for the Faraday law also we write something like this. E dot dl is equal to, what do you write as? D phi b by dt. So this field is created by what? What is creating field here? Electric field is created by what? Change in magnetic field flux. The magnetic property is creating electrical property. Anvita, what did you say now?
It's due to the magnetic field.
It's magnetic, you see, changing magnetic field. No, not only magnetic field, what is required here? Changing magnetic field or varying magnetic field creates electric field. Now what he has proved now, what has Maxwell proved that one? Changing electric field creates magnetic field. So both are, so what is it? That's and that proves the symmetry between electric field and magnetic field. Okay, let's suppose, so what he had done, one part, if we just look at one part, we have seen what is the modification in Ampere's law made by Maxwell. He added the concept of displacement current, which is equal to conduction current. It is uniformly distributed over plates of the capacitor. It is equal to, and that displacement current produces same effect as conduction current in terms of producing magnetic field. So we can calculate magnetic field due to displacement current, treating as equivalent to conduction current. And in terms of formula, we have arrived at very simple formula, because that's only case we come across. Only case we can calculate magnetic field is when the symmetry exists. And symmetry will exist only when the plates are circular in shape. And we use, so magnetic field can be calculated using BM concept. All points can be calculated. Now let's come to some application. I'll go through some questions based on that. Okay, correct. First question. What is the RMS value of displacement current? What is the first thing I should come to my mind? What is RMS value of displacement current? First thing we should come to my mind, okay, displacement current is equal to conduction current. What is the RMS value of a current? What kind of circuit is this? This is an AC circuit. AC supply source connected to capacitor. So do I know the formula? How do I calculate AC circuit? How do I calculate current? What is RMS current equal to? What is RMS current equal to? VRMS. Actually, this formula is valid for all kind of AC circuit. But if only capacitor is connected, the impedance is equal to only XC. That's the formula. So do we know every term here? V term is known. Do we know XC here? C value is given, omega value is given. You can easily find out RMS current. Next question. In this case, what is given here? This is a DC source is connected. In this case, what does it imply? A capacitor, if a separation is given, area is given, I can calculate its capacitance. If it is connected to a source of 400 volts, it's a DC source. It will acquire a charge Q equal to CV. And thus a charge capacitor will acquire, but it will not acquire instantaneously. This charge in this question, what it implies, this charge is acquired over so much of time. So what is the current which has shown? The current is equal to delta Q by delta T. What is delta Q? Initially charge was 0, total charge acquired was CV. CV by delta T becomes my conduction current. And this is equal to my displacement current. So implies charging is done uniformly over 10 to the power minus 6 seconds. So rate of charging I is equal to C into V by time, which is 10 to the power minus 6 seconds. Let us solve a substitution. What is the magnetic field between plates of a capacitor for R is greater than R? What is magnetic field between plates of a capacitor? Kathy, can you tell me what is the magnetic field between plates of a capacitor when R is greater than R? Okay, Kathy has been, she has told no several times. Gayatri, can you tell me what is the magnetic field between plates of capacitor? R is greater than R. Gayatri?
Yes, sir.
Can you tell me the answer for this? R greater than R.
U naught ID by 2 pi R square.
2 pi r only. So this formula, any point outside is same as wire equation. What is the wire equation? If I have infinite long wire, what is the field it creates? R greater than R, field formula is same as mu naught I by 2 pi r, which you know. This is directly formula. Only thing what has happened, there we calculate for conduction current, here it is for displacement current. Both are same. They are pretty simple. Okay, condenser is being charged using constant current. So the current is constant. Ratio of magnetic field at a distance of r by 2 and r is pretty simple. Ratio of magnetic field varies linearly. So this will be half of this, very simple. So B at r by 2 will be equal to half of this linear variation. So this is very simple, 1:2 ratio. Magnetic field between circular plates of radius is given and separated by distance. Whenever radius and distance are given, actually we can calculate capacitance using E epsilon naught by D. Capacitance can be calculated. Having capacitance is given. Okay, it is done. What we need to calculate? Along the axis. What is the magnetic field along the axis? Shreya, can you give me an answer for this? Shreya?
Yes, sir. I'm reading.
Yeah. Now, what is the magnetic field along the axis of the plate? What does axis of plate mean? What is R equal to when it is along the axis? What is R equal to? What is the distance of the point from the axis? So we have to calculate magnetic field at a point lying on the axis of the plate, which is R is equal to 0. What is the field at R is equal to 0, Shreya? What is the field at R is equal to 0?
0.
0. It varies linearly at origin is 0. This is a very pretty simple question. Variation of induced field. This thing, what is the as a distance from the axis? How is the field varies as a distance from the axis? We already see it is very linearly. This question, how would you calculate? Just all of you read this question. Electric field in the gap of a conductor, charges are this. What is given here? dE by dt is given. Rate at which electric field is changing. Well, sometimes you can understand better from units. This is the unit of field, volts per meter. Potential gradient is field divided by S. dE by dt is given. Rate at which electric field is changing. If electric field is changing, flux is changing, there's a displacement current. Radius of each plate is given. Find the magnetic field at the edge of the plate. How do we calculate? In this case, conduction current is not given. So in this case, we know what is the formula for field on the edge of the plate. Formula for field, what is ID? So basically, how do we calculate ID? Conduction current is not given. We have to calculate using basic definition of ID, which is epsilon naught into d phi E by dt. What is flux equal to? Electric field flux is E into A. All cases we are taking area perpendicular to the field. So area is constant, it becomes epsilon naught A dE by dt. Do we know all the terms here now? Once you get ID, then I can calculate B also. What is B will be equal to? Mu naught ID by 2 pi R. What is D by dt here? This is a term which is nothing but D by dt. Electric field in the gap is changing at this rate. Wordings are not very clear. Perhaps they should have mentioned the electric field between the gland and condenser is changing at the rate of so and so per second. So this value what is given is d by dt. If you spot that one, that's the case. In this particular case, I need to use basic formula for displacement current. It's epsilon naught times d phi by dt. Read this question. Okay, so I'll just stop here. I'll continue from here in the evening session. And again, as mentioned earlier also, I expect all of you to join. We'll continue with this, and I'll also start with something about traveling wave concept. I think probably I'll explain that concept also today. So be there for the class, all of you.